Remember that time I made a video about Toslink? I sure do. It was just last week. Almost. Well, before I ended that video, I left you with a question. Why haven't we seen fiber?
You've angered the hi-fi gods!
Bang!
When two basketball players love each other very much, they suck each other off, and Jimmy must love the Nuggets because he's the only one sucking.
Because it is connected to ground, if there's an imbalance between the two grounds of the sending and receiving equipment, that creates a current in the ground of the signal wire, which can affect the analog amplification circuitry. Because Toslink is an optical signal, the two devices are galvanically isolated, and it doesn't matter in the slightest if there's a ground imbalance. Toslink is, in effect, an optoisolator, and this benefit should not be ignored. Now, I would like to provide an explanation for my careless oversight. For every person who touts the benefits of Toslink, there's another that complains about clock jitter. Those individuals claim that if you're encountering a ground loop, for the love of God, don't use Toslink with all its totally real imperfections. Sort out that problem, you heathens! Audio forums are worse than Twitter. Each of you likes what you like, and anytime anyone presents any opinion regarding the pros and cons of one system or another, y'all lose your minds and get real pretentious, and I'm just kinda over that. I, admittedly, chalked up the concern for ground loops to be one of those opinions. But it's not. Toslink can, does, and has many times presented a meaningful solution to the problem of ground loops or other electrical noise issues, and it may in fact be the entire reason Toshiba developed it. It is interesting to note, however, that the ground loop problem seems to have gone away in the age of HDMI. Whether that's down to better isolation inside the equipment itself or some other thing, it suggests that the problem could have been solved without going to an optical fiber. It may have just been easier, and let's not forget cooler, to use Toslink. Alright, now that that's taken care of, let's get back to the question at hand. With Toslink being developed in 1983, why haven't we seen fiber...
You've angered the IT!
Bang! Why haven't we seen fiber optics in the consumer space aside from Toslink? Actually, in some very niche circumstances we have, and your average consumer is familiar with things like USB, HDMI, DVI, DisplayPort, Thunderbolt, Cat5 cabling with 8P, 8C, often incorrectly referred to as RJ45 connectors, and maybe FireWire or SATA or perhaps other things. All of these use wires like some sort of technologically regressive lazy person. Why not use light? Well, let's start with the obvious thing. Toslink works great for connecting pieces of audio-visual gear together because each one will have its own power source. All that needs to get sent between them is a little bit of data. But lots of things need power, too. Have fun using that keyboard and mouse connected to your computer by nothing but light. And as we moved away from the days of RS-232 serial connections and into the holy land of the universal serial bus, suddenly we found that we're not sending little bits of power just to keep your mouse alive. We're sending loads of it. I don't want to go off on too much of a tangent here. Oh, who am I kidding? I do this all the time. It seems like USB turned into the power delivery standard it is today, kind of by accident. Remember that even in USB 2.0 days, officially a device could only draw 2.5 watts, and that was considered high. In those wild days, different companies were coming up with their own ways to determine the current a given port could supply. And it wasn't until 2007 that the first USB battery charging specification appears, finally getting everyone on the same page and allowing for USB ports on computers to finally, officially provide more than 500 milliamps when asked nicely. Anyway, now that USB is ubiquitous, we can expect any modern device to provide a decent amount of power through its USB ports for things like portable hard drives, charging your phone, and of course the monumentally important task of powering all those RGB LEDs in that gaming keyboard you bought because, you know, +5 agility. But you may recall that the switch from USB 2 to USB 3 didn't just involve making the data transfer go faster. The 4 conductors of the USB cable weren't enough, so we had to add more of them for USB 3. 5 more to be exact. Add too many more, and we might as well just start using HDMI for everything. But with fiber optics, we could potentially have much, much faster data throughput using only a pair of optical fibers, or potentially just one if you, for instance, send data in each direction using 2 different wavelengths of light and separate them with a prism on each end. So, sure, we need to send power to devices in addition to data. Why not create some sort of composite cable? No, not that kind. A cable that is a composite of both optical and electrical. Like a USB cable where the data lines are replaced with optical fiber. Then, the same cable could be used for nearly everything. All we gotta do is just make the LEDs go blinky blinky a little faster, and we could have been using the same cable since the 80s. Well, not so fast. not so fast. Optical fiber is complicated. It doesn't seem like it should be. After all, what are we really doing but flashing a light source and moving it somewhere else so we can see the flashing and decode it? But thanks to physics, it's not actually as simple as that. Stupid physics making everything more difficult. I don't want to get too far down this particular path because its importance to potential consumer standards is arguably minimal, but it's important nonetheless. Since light travels at the speed of light, it may seem as though a pulse of light down an optical cable will reach the other end in exactly the same way that it was sent. But it won't. Thanks to a phenomenon called modal dispersion, also known as multimode distortion, multimode dispersion, modal distortion, intermodal distortion, intermodal dispersion, and intermodal delay distortion. Geez guys, pick a name already. The signal actually gets a little smeared. Let's imagine we send a pulse of light down this optical fiber. Will it all get to the other end at the same time? It seems like it should. It's light, after all. But just because something happens as fast as we know things can happen doesn't mean geometry doesn't apply. If the individual photons in that pulse of light manage to stay perfectly parallel to the sides of the fiber, they will all arrive at the other end simultaneously. But this is the real world, and nothing's perfect. Some of them are going to enter the fiber at an angle, which means they don't take a straight path. They bounce off the sides, and although total internal reflection keeps them from leaving the fiber, this zigzag path is much longer than a straight line. So those meandering photons will in fact arrive later. And this limits the speed at which we can pulse the light on and off and still have it be intelligible on the other end. This is that smearing of the signal. Even though on the sending end we're putting in a clear-cut on-off signal, on the receiving end, the photons who lollygagged and bounced around in the fiber cause the signal to look like this. Some of the photons from the last pulse manage to arrive at the same time as some of them from the next one. So we have to limit the frequency at which the pulses happen in order to make the received signal decodable. This means that optical fibers do actually have a bandwidth limit. Just because we're using fiber optics doesn't mean we have theoretically endless upgrade capacity. That said, you might have already surmised that the bandwidth limit depends on how long the optical fiber is. No matter how poorly the light behaves in the pipe, if it's a short pipe, then the time difference between straight and true photons and disastrously off-course photons is quite small. And this is why discussing the bandwidth limitations of a given optical fiber is not really a big deal if we're dealing with consumer applications where cables aren't likely to go beyond 10 meters. But since it's interesting, let's get into how we deal with bandwidth limits anyway. In the land of fiber, there are two basic kinds of fiber optic cabling: single-mode fiber and mode fiber. Now, mode here doesn't mean a method of operation. Here it means the field pattern of propagating electromagnetic waves. Ideally, we want the light to travel only in the transverse mode, and that's what single-mode fiber allows us to do. It accomplishes this by having a very small internal diameter, what we in the business call itty-bitty. Generally, it's between 8 and 10 micrometers across. This tiny size of the fiber allows the pulses to remain distinct over longer distances because the light traveling through the fiber mainly stays in the longitudinal mode. Because of this, long-distance links on the order of thousands of kilometers are usually done with single-mode fiber. But single-mode fiber is really finicky to deal with, requiring special tools to make connections since it's so darn small. So for applications involving shorter fiber runs, like networking a building, we'll use much easier to deal with fiber. This thicker fiber allows us to make cable terminations more easily at the cost of a messier signal on the other end. Still, it's a fair bit of bandwidth. Using just LEDs, gigabit speeds are easily achievable, and if we get into higher grade fibers and start using lasers as transmitters, we can get 100 gigabit speeds over distances on the order of 100 meters. And remember, the shorter the run, the easier it is to achieve high bandwidth. But if we're talking about a fiber like Toslink, well, that's nothing like even multimode fiber. It's actually in a third category. Generally, Toslink is a plastic optical fiber. It's much thicker inside, about 100 times thicker than single-mode fiber, so it exhibits much greater modal dispersion, and thus its bandwidth limit is much lower. But how much lower is it really? I mean, shorter lengths make the bandwidth go up, so even though that fishing line in there has wicked bad modal dispersion, over just a few meters it shouldn't matter much, right? Right! In a 2009 paper by Yasuhiro Koike, the possibility of using plastic optical fiber for high-speed networking was explored. By using different modulation methods, it was found that plastic fiber could easily achieve gigabit speeds at lengths up to 100 meters. And with the development of graded index plastic fiber, 40 gigabit speeds were achieved. Pretty impressive. But now we're stepping into messy territory. Let's rewind a bit. Graded index plastic optical fiber is a new development. And the question I'm getting at here is, why haven't we been using fiber forever? Imagine that in 1985 we had come up with one standard cable, like a bidirectional toslink cable with a pair of power wires running through it. I'll call it Unilink.
In 2019, I bought a cheap A-model PS3 on eBay. It was described as having the yellow light of death. My own journey was full of bad advice and pitfalls. I made all the common mistakes. That was the trigger that consumed my PP. This is my journey to fixing the PS3. In September of 2020, I bought my second Yellow Light of Death PS3, another backwards compatible launch model. I'd been lured in by the NEC token hysteria. Basically, these are special kinds of capacitors used in the PlayStation 3 to feed clean power to the CPU and GPU. Then a tutorial was posted on the PSX Place showing the tokens could be the problem and how to replace them. But most of all, regular people were reporting it worked, and YouTube videos started showing consoles coming back to life. It looked like a simple do-it-yourself repair. It was exciting. It was a great narrative. It was too good to be true. The idea that capacitors were the problem all this time felt like liberation from